In my previous presentation, we took a look at the basics of differentiation and looked at how to find the derivatives of polynomials. On this presentation, we're going to go that a little bit further, and we're going to take a look at some basic trigonometry functions and natural log functions and exponentials. But before we start that, I just want to show you this table. So this is a table of derivatives. So this is your basics, really. These are probably all you'd ever use, really. I obviously got this from the internet. It's produced by mathscentre.ac.uk, which is part of the Pearson's publishing group, but there's loads of these available. Just Google it and you'll find tables of derivatives everywhere. The ones we did in the last presentation and the functions I'm going to cover in this presentation really should be committed to memory. So you shouldn't really need to resort to this table of derivatives to do them. It should become second nature, because basically these are the common building blocks of finding derivatives. Okay, so let's move on. I'm going to start with a couple of basics. So the sine function, sine of x. Now, of course, it doesn't have to be x. It can be any terminology that you use for the variable. Quite often we use the theta symbol to represent angles. In this case, I'm just going to use x just because it's that little bit easier to put in, to be honest with you. So we're going to have y equals sine x. So what's the derivative of that? Another thing I need to say at this point as well is when you're dealing with trig functions, as I'll shorten the name down to from now on, trig functions, they've got to be in radians. So if you're doing anything with differentiation or anything with calculus, so that integration as well, of course, then you've got to work in radians. So there's no degrees. Obviously, you can easily convert degrees into radians, and so then you set up perfectly to go ahead and do it. Okay, so these are nice and easy. All you got to do is remember that it's going to be, if you've got sine, it's what I tend to call the other function. So we've got dy over dx. So if you remember, y is our first term, x is what our variable. So we write it in this style. Okay. And as I said, it didn't have to be an x. It could have been theta, for example. It could have been t, if it was. Quite often is when we're working in radians. Omega t or 2 pi t or something of that nature. Anyway, I'm going to use x for now. So it's quite simple. It's the other function, so it's cosine. I know it's not strictly speaking the other function, it's just another sine wave that's got a 90-degree phase angle, but just for sake of simplicity, we'll call it cos. And it's cos x still. And that's simply it. So you'll see this in the table of derivatives. If you're doing a derivative of sine x, it's just cos x. Now cos often has the habit of being that slightly awkward version. Dy dx. Find the derivative of this. It's the other function again, sine x, like thus, but the complication is it has a minus sign in front, so it's minus sine x. So dead simple, really. So it's just a case of remembering sine becomes cos becomes sine, but it has a minus sign. So moving on to the next bit. Now I've added another level of complication here. We've got 3x in the brackets. So let's have a look. So it starts off fairly similar. So dy dx equals, again, the opposite function, so-called. Now the thing to remember is the stuff inside the bracket stays the same. Okay. So just remember that. Whatever inside the bracket stays the same. Now the difference this time is this 3 is now copied out. We'll call it copied to the front. So 3 cos 3x. If there was any number out front, like a 2, then you would just multiply it into that. So you'd have 3 times 2 would be 6. So if you have to look at the cosine function. So again, it becomes the other function, so-called, by me. Sine, the stuff in the bracket stays the same as before. Now you remember that it's a minus sign, and again 3 copies out to the front. Simple as that. Very easily done. Okay, moving on to the next one. Next examples. So that's it actually. Those are finished. There's not really much more you can say about them. The x could have been divided by 3 instead of times by 3, but it's exactly the same. It would be basically x times a third, so the 3 would pop to the front. I've just realised I made a mistake here, by the way. That should be 5 there. Let me just correct myself. Well done to anybody who spotted that. That should have been 5. I like to pretend that I do these mistakes on purpose to see who's awake, but obviously I'm not going to fool you guys. Okay, so ln, natural log. Now obviously there's different kinds of logs. Let me just give a very brief background. I assume you know all this, but a natural log really means logs to the base. Is that when you look on a calculator, you've got 2 log functions, an ln, as here, and then you've got this one. And when you've got this one, it normally means it's to base 10, like thus. But what it means when you've got natural log, it's not base 10. Let's cross that out. It means it's to log e. Okay, let's do this properly, I think. Okay, get my pen back on. So it's it means exactly the same as that. So it's logged where the base is e, and I'm not going to go any further into that. I should have put this an x here. It's be my guest to look into that further on other YouTubes. Okay, so that's what it means when we're dealing with logs. When we're dealing with calculus, again, there's a rule here. We've got to use natural logs. Obviously, again, like you could do with degrees, you can convert degrees into radians. You can also convert other bases into natural logs, and there's a method of doing that, and that's something for you to do as homework to look up. Okay, so what would this become? Well, it's quite easy actually. So it's dy, so I should have a y equals out front here, but never mind. Dy dx equals, it's very simple, 1 over x. Simple as that. Now if you've got a number in here, dy dx, the answer is 1 over x. That easy. What actually happens is it becomes, I'll do it over here, it becomes actually the 2 goes to the top and you have a 2 at the bottom, 2x, which of course is the same as 1 over x. And if this number was another number, that it'd just do the same thing. If it was 3, it'd be 3 over 3, 3 over 3, so it'd become 1x. If it was a billion, it'd become a billion over the billion x, so it'd be 1 over x. So it's the same thing, so that's nice and easy. That one's not actually in that table of derivatives, so it's worth making a note of that. If you print that off, then maybe write it on the side. Incidentally, if you've got a number out front like this, then that's not going to disappear. That'll stay there. That'll come out to the front of your answer. So you would have, I'll put it in brackets just for clarity. So you'd still have that result, 1 over x for the two part, but the 2 out front would stay there, come out front still, and that obviously would simplify to 2 over x. Don't confuse these two things, they're different. Okay, nice and easy still. Moving on. On this one, we're going to look at the function of the exponentially, which is probably more familiar as Euler's number, spelled like this. Well, it would if it worked. Try that again. Must have gone too fast for it. Euler. So you might be tempted to say Euler, and nothing wrong with that, of course. But Euler was a Swiss German, so it's a German pronunciation of the name, so it's Euler. He was one of those great mathematicians. If you had to name your top 10, he's definitely in there. In fact, he could even be in the top 3. It's named in his honour, but he didn't actually develop it to discover this function exponentially. It was one of his friends whose name's just gone out of my head. Never mind. But Euler's number E is equivalent to 2.718. Was it 28, 28, 18, 28, 45, 90. I'm just showing off now. Okay. And it's what they call an irrational number. So it keeps going. It's got no end. Obviously, I'm not that clever. My memory's not that good, but I just remember the first 4 digits, and then I know after the 18 it's 28, and then it repeats. So 18, 28, 18, 28. And then if you remember 45 degrees, 90 degrees, 45 degrees, you can look like you're the right smart Alec. Okay, so that's the secret to that. So it's a function. It's linked to, as in the previous slide, it's linked to natural logs. It's the base for natural logs, and it occurs in nature. And I'm not going to say any more. I could do, and I'm not going to do. If you want to look into it, there's a lot of stuff on YouTube. Well worth actually reading about his life and his work. Really is. Or maybe I'm just a geek. I don't know. Right, to the task. So y equals e to the x. So dy dx equals. Okay, be careful now. Listen very carefully. The answer is e to the x. So it's the world's easiest differentiation, and it proves to be the world's easiest integration as well when you come to that. So that is it. It's e to the x. Simple as that. Nothing changes, and there's good reasons for that, good mathematical reasons, which I'm not going to go into. This one, what happens if there's a number out front? Simple. The 7 comes down to the front. Now this is the thing you've got to be careful about. Because you've done the polynomials, you may feel that you need to take 1 away from the 7. Don't do that. It's wrong. It stays. It's a bit like the sine function, cosine function. It stays the same. It just copies down to the front. Simple as that. This one, same thing. It might look a bit more complicated, but it's not. The only thing complicated about it is using negatives. That's all. Take the 7 down to the front, which is a -7, note. Multiply it into the front, we get -14. And the stuff at the top stays the same. Another way, minus, stays the same. I said and then contradicted myself. Another way maybe looking at it is you should, strictly speaking, write this in brackets. If you look on a lot of calculators, they actually put it in brackets when you use this function. And that's the correct way of putting it, really. Okay. Now the bit I know you've all been looking forward to, your turn. So if you want to pause the video, have a go at them, restart the video, and I'll go through them for you. Okay, so welcome back. So hopefully none of these are too difficult for you. First one, I'm not going to write the dy dx every time. This gets a bit long-winded. I'll just do it on the first one. And another one soon that you'll see what I mean when I do it. Simple enough. Cosine x. This one you'll know. Now note here that I've used a different variable term. So the correct way of writing it is theta. That's just simply cos becomes sine theta still, but of course it's got a minus sign, so don't miss that out. Okay, next one, log x, easy one. I'll just go straight to the equals. It's not mathematically correct, but I'll just do it for brevity. One of my favourite words, brevity. Do everything as easy as possible. Next one you all know, e to the x. The next one, a bit more tricky. Now the way I suggest you go at these is do what you know first and work backwards to the more complicated, if that makes sense. You'll see what I mean. Cosine, whoops, that doesn't make sense. I'm just going to let's erase that. Okay, back to my writing. Okay, so it's sine. Remember, everything in the bracket stays the same, so do that next. We know it's going to become a minus sign, and the 2 is going to copy out to the front and multiply into the 2, so we're going to get 4. Excuse me, minus 4 sine 2x. Okay, right, a little bit more involved, maybe a little bit more thinking these, but remember what I said, whatever's in front of the x, it still gives you the same, 1 over x. So that's not as difficult as it looks. Next one. Okay, 3 exponentially Euler's number 5 to the x. So take the 5 down to the front, multiply it in 15e, and the stuff at the top stays the same. So that's nice and easy. And then I've saved the best to last. So my dependent variable is the s, so it's going to be ds. If you remember what I said in the last video, this is basically, the d means a small change, so it's rise over run basically. It's finding the gradient. Our other variable is t for time, usually. Okay, so you've got to use the right terminology. Okay, and it's going to be ds over dt. So again, do it the easy stuff first. So we know it's going to be the other function, sine. The stuff in the bracket stays the same, t divided by 4. The number out front, we know, right, now normally cosine becomes minus, but this has already got a minus sign, so this actually must be a plus. I'm going to put a plus there just to emphasize that. And remember, don't be fooled by this or put off by this. It just means t times 1 over 4. So basically it's divided by a quarter. Not divide by a quarter, divide by 4. So like that, which if I simplify just becomes, oops, not that, 2 sine, and then let's put my brackets on, t over 4, and that's it, done. So that's about as hard as they get, really, just about. But if you take your time, be careful of the signs, the minus signs, they're the trip up points. Wait while you get to integration, then you'll really find out about being tripped up by minus signs. But anyway, they're fairly straightforward. So thank you for listening.